Okay. Well, good afternoon, everybody. Good afternoon. Can everyone hear me? Delighted to have you here on this rainy afternoon here in Philadelphia. I am David Cole, president of the Science History Institute. Welcome to our Joseph Priestley Society January lecture. We are delighted, I want to underscore that, delighted to have such a robust audience joining us both online, but also in person. I think it's been some time that we've been able to do this in person for our Joseph Priestley lectures. And so we're thrilled really that you have braved the rain and the elements and joined us here this afternoon. This month's Joseph Priestley Society presentation is our annual Ralph Connor Memorial Lecture, which was created by the Science History Institute to showcase periodic addresses on the role of research in the development of technology and industry by eminent practitioners in the chemical and molecular sciences. I would also like to thank our JPS Executive Committee who organized this series. Thank you all very much. This afternoon's presentation is by Roger Turner, the curator of instruments and artifacts here at the Science History Institute. And I believe, I'm told this is Roger's fourth time gracing this body with his wisdom. So we're really delighted to have you back, Roger. Roger studies how the often invisible labor of scientists and environmental observers shapes daily life. He helped launch the student role-playing game Science Matters, The Case of Rare Earth Elements. He worked on the film The Instrumental Chemist, developed the playful online experience Instruments of Change, and he contributes to museum exhibitions here at the Institute. He wrote and curated Critical Metals, The Chemistry of Light, and Mechanochemistry, The Science of Crush for Google Arts and Culture. Please check out his work on our website, sciencehistory.org. We will be taking questions at the end of Roger's talk. For those of you who are online, please do type your questions into that chat and we will absolutely come to you for your questions. For those here in person, please do feel free to step up to the mic after the lecture and we will recognize you. And now, please join me in welcoming Roger Turner to the stage. Thanks.
Well, thank you very much. It's a treat to be back here in person with all of you and to be joining you wherever you are for people who are tuning in remotely. I hope I will entertain you while you wash dishes or fold laundry or do all the many things that I have done while listening to other people lecture over the last few years. So today, today magnetic resonance imaging is a widely used medical tool mentioned in the news reports anytime a high-profile athlete twists his knee or grabs her elbow. But the development, this is just an example picked literally at random on when I was making the start of the slides a couple weeks ago. But the development of MRI was far from straightforward. And I'm going to take you through a hopefully fun telling of this history today and end by reflecting a bit on what we might learn from that history. And I'm particularly interested to hear at the end your thoughts on how we might continue to tell this story of the history of NMR and MRI. So let's start with a really basic question to get us on the same page scientifically. What is NMR? So quick definition, kind of as we know it today. Nuclear magnetic resonance is a physical phenomenon in which nuclei in a strong constant magnetic field are perturbed by weak oscillating magnetic field, and they respond by producing an electromagnetic signal with a frequency characteristic of the magnetic field at the nucleus. Put it a little different way, the strong magnet aligns the quantum spin of the protons and the neutrons that make up the nucleus, while the oscillating field generally distorts this alignment. Well, all right, how about at a really simplified level for everybody who doesn't run an NMR facility at a local university, who I know there are such people in the audience. So think of it this way. You've got a sample sitting next to a strong magnet with some wire around it that can induce a changing magnetic field. You change the field in there back and forth, and you can adjust the frequency of that change. The nucleus of the atoms in there, those protons and neutrons at the center, they respond to that change by emitting a radio signal. At certain frequencies in the changing magnetic field, you get a spike in the radio signal. And by measuring those spikes, you can learn more about your sample. Don't throw any tomatoes, but that's my real basic level. But of course, not all nuclei can be perturbed that way. To respond to nuclear magnetic resonance, a nucleus has to have an odd number of protons and or neutrons for spooky quantum reasons that I'm not going to talk about because there may be kids watching. So only some isotopes of atoms can be studied this way. But as it happens, hydrogen-1 and carbon-13 are particularly good in this respect. And since these nuclei are super common in biological molecules, NMR has proved to be very useful for organic chemistry and medicine. And what's more, of course, electrons also come into play here since their small local electrical fields add to or subtract from the external magnetic field, and they can partially shield the nuclei. So for example, a hydrogen atom, when it's bonded to an oxygen atom, will shield the nuclei differently from a hydrogen bonded to a carbon atom. So what that means is you can also use NMR to understand molecules and bonding as well. So we're getting a little ahead of ourselves here, so let's get back to history. The first steps in the discovery of NMR were made by Isidore Rabi at his lab in Columbia University during the 1930s. Now, as a teacher, as we see him here, Robbie was dreadful. As the Nobel laureate Leon Letterman remembered it, after a lecture, the students would all head over to the library to try and work out what Robbie had been talking about. Or as the MIT nuclear chemist Irving Kaplan put it, he called Robbie one of the worst teachers I ever had. But as a leader in physics research, he was brilliant. During the 1930s at Columbia, he and his students were measuring nuclear forces with ever greater degrees of precision. Robbie was working with a molecular beam, right? So this sort of highly evacuated environment in a near vacuum where individual beam molecules are separated from each other. So you can almost look at one molecule at a time. In early 1938, the team published its discovery of the magnetic resonance method in lithium compounds. And then applying this method to hydrogen atoms, which are composed of just one proton, they calculated the magnetic moment of a single proton. Switching to deuterium, an isotope of hydrogen that has one proton and one neutron, they were able to calculate the magnetic moment of a neutron. These calculations helped reveal the forces that hold together the components of the nucleus. And for this work, Robbie won the Nobel Prize in Physics in 1944. But nuclear magnetic resonance isn't the same in bulk matter, right? That kind of aggregations of molecules that you and I are made of. It was two different groups of physics working separately at almost exactly the same time at the end of 1945, who worked out how to induce and measure nuclear magnetic resonance in bulk matter. At Harvard University, Edward Mills Purcell and his colleagues worked with a block of paraffin wax. And across the country at Stanford, Felix Bloch, William Hansen, and Martin Packard worked with a sample of water to measure a signal coming from the nuclei of hydrogen atoms. Now, it wasn't immediately obvious that both groups were actually measuring the same things. And they adopted different terms to describe what it was that they had measured. So the Stanford team called the phenomena nuclear induction, while the Harvard team called it nuclear magnetic resonance. Apparently, for some years after, you could tell whether or not a physicist was from the East Coast or the West Coast by which of these terms they used. Ultimately, the Harvard language prevailed, but it's the Stanford team that we're going to follow because they move our story along. So let's explore how nuclear magnetic resonance became an important tool in analytical chemistry. So it was immediately clear that measuring nuclear magnetic resonance in bulk matter was going to be a big deal scientifically. Felix Bloch and Edward Mills Purcell shared the Nobel Prize in 1952 for their leadership in this discovery. And while it was physicists who had led these initial investigations, the phenomena was clearly of interest to chemists as well. top-end academic departments around the country began to build or acquire the equipment to measure NMR. And initially, though, these instruments were hard to work with and not very robust. And a great example comes from the Institute's oral history collection, where the interview with chemist Mildred Cohn. So here's how she remembered one of the first NMR instruments she worked with. When I came back from sabbatical in 1956, nobody then had a commercial NMR instrument. They had a home-built one in the chemistry department at Washington University, but it could only do proton spectra. It was unshielded, and it was so sensitive to external perturbations. The students showed me one day. They had a peak on the oscilloscope, and then they took a pair of scissors and opened it, and the peak disappeared. They had changed the magnetic field enough to make the signal disappear. So what changed in terms of making the NMR into a stable and more useful chemical instrument was largely the work of the company Varian Associates. Now, Varian was a high-tech firm that was born out of the Stanford Physics Department in 1948. It was one of the original residents of the famed Stanford Research Park, so it's understood today historically as a key player in the emergence of Silicon Valley. But Varian was founded by, among others, the brothers Russell and Sigurd Varian, as well as Leonard Schiff, who was at the time the head of the Stanford Physics Department, and William Hansen, who was, of course, one of Felix Bloch's collaborators on NMR. As the historians of science and technology Tim Lenoir and Timothy Lecuyer argue, these men sought both a source of reliable funding for research, plus a space where they could do R&D on classified military technologies, the kind of work that couldn't be conducted in an open academic environment. So the company initially developed an advanced Klyston, part of the specialized electronics used in missile guidance systems, kind of a really big fancy vacuum tube, while working to commercialize NMR instruments. Russell Varian had convinced Bloch and Hansen to apply for a patent on their NMR method. They hadn't initially thought to do that. And Varian Associates became the exclusive licensee. Bloch worked as a paid consultant to the company, while his graduate student, physicist Martin Packard, was one of a number of Bloch students who went on to work for Varian. Now, Varian cultivated a research culture that was in many ways quite similar to that of Stanford. It hired postdoctoral researchers, expecting them to return to academia or move on to other firms after a couple of years. Their staff attended academic conferences, presenting symposiums, publishing papers. And the Varian's research staff cultivated relationships with academic scientists, both learning what it was that those researchers wanted for their research, but also shaping what professors were interested in and what kinds of tools they thought would be useful for pursuing their research. It's kind of what in history of science we call mutual shaping. And as Mildred Cohn remembered it, that period between 1956 and 1958 was the moment when NMR research really took off amongst the organic chemists. Now, she herself was interested in studying the phosphorus in adenosine triphosphate, right? A key molecule in cellular metabolism. In 1956, she had heard that Varian had developed a probe that could measure phosphorus 31. And she wrote to them, and Varian enthusiastically invited her to come out to Palo Alto. But as she put it in her oral history, by this time I had 3 children. They were all fairly young, and I couldn't just pick up and move out there. So it wasn't until 2 years later, when her husband started a visiting professorship at Stanford, that she was able to go. And as she said, in those 2 years, the organic chemists had discovered NMR, and now Varian was selling instruments, and their application laboratory was very busy showing people what you could do with it. Fortunately, she met Felix Bloch at a barbecue, and he invited her to come along with him, and his recommendation got her the time she needed on the instrument to do her research. And it was Varian's release of the NMR, the A-60 spectrometer in 1961 that really marked the moment when NMR became accessible as a routine method in analytical chemistry. As this Varian ad put it, the A-60 featured, quote, a new design approach which provides completely reproducible spectra on pre-calibrated charts. So chemists could not only use the machine to create their own structure determinations of unknown molecules, or known molecules that they were trying to work out, what the structure were, how they all fit together, but they could also compare the spectral fingerprints of unknown molecules to an expanding library of standardized NMR spectra. Now, while the A-60 really was a fantastic advance, it wasn't quite as easy to use as the ads touted. A couple of the labels that users stuck on to the A-60's operator console that we have right over there in the museum give you a sort of suggest the difficulties that users encountered while working with it. So I'm going to check out these two stuck on labels here. So the less fun warning card explains that what the operator needs to do in order to keep the spectrometer's magnet functioning properly. So the instrument had a 3-foot high, 2,000-pound electromagnet, which we don't keep in the museum. It's off in a warehouse in New Jersey. Not that interesting to look at, but very heavy. But it needed to be kept cool by water circulating through a coil of pipes. And so as the label explains at the bottom there, it says, do not turn off the water unless you are prepared for the magnet to shut off. But this is the warning label I really love. This is the more fun one. It reads, warning, this machine is subject to breakdown during periods of critical need. A special circuit in the machine called a crisis detector senses the operator's emotional state. In terms of how desperate he or she is to use the machine, the crisis detector then creates a malfunction proportional to the desperation of the owner. Threatening the machine with violence only aggravates the situation. Likewise, attempts to use some other machine may cause it to malfunction too. They belong to the same union. So keep cool, say nice things to the machine, because nothing else seems to work. One of my hopes is to create a digital exhibit called Jokes and Warnings, labels found taped to scientific instruments. Okay, so how did NMR move from an instrument of the analytical chemistry to MRI, right? A tool that could be used to scan Kevin Durant's twisted knee. The story here that I'm going to tell next is about the deliberate misuse of the instrument by a guy working at night at SUNY Stony Brook. And it was really kind of the stories told by Paul Lauterbur that first got me interested in researching this topic. All right, so here we go. So according to Lauterbur, he first came up with the idea for magnetic resonance imaging on September 3rd, 1971, when he was a student and researcher at the University of Pittsburgh and the Mellon Institute for Industrial Research. He was eating a hamburger at Big Boy's restaurant when he scribbled on a table, the moment of inspiration struck, and he scribbled down on a table napkin his first ideas for the MRI. Then, of course, as a good scientist, understanding concerns about priority and about how you establish your ideas, he ran off to buy a notebook where he more formally described his idea. And of course, he signed it and had it signed and dated the notebook, each page, and had it witnessed. And today we have that notebook up in the archive. So you can come to the Othmer Library and look at it, or go online to our digital collections where we've scanned every page at extremely high resolution. You can download like 20 megabyte files for every page and read it to your heart's content wherever you are. Now, Lauterbur used the ideas of Robert Gabillard, who had developed them back in 1952, of introducing gradients in the magnetic field, which allows for determining the origin of those radio waves emitted from the nuclei. And this spatial information, in turn, makes it possible to make two-dimensional pictures instead of just one-dimensional spectra. So after that inspirational hamburger, Lauterbur went on to get a faculty job at SUNY Stony Brook. And the best machine on campus belonged to the chemistry department. He had to go over to visit it at night to use it for his experimenting. And what he did is he skewed the settings to produce a gradient rather than a uniform magnetic field, what otherwise would have been a rookie mistake for an operator. not wanting to give away what he was doing to the machine, at the end of the night, he would carefully go back and change the settings so that they were back to what the chemists would have expected when they, people who were supposed to be using the machine came in the morning. And the first thing that Lauterbur imaged was a tiny baby clam, actually, that his 9-year-old daughter had found for him on the beach in Long Island Sound. It was just small enough to fit into the small magnetic aperture. And of course, it was perfectly happy to sit still. Lauterbur also imaged 2 test tubes of heavy water that were immersed within a beaker of ordinary water. That was the sort of thing that no other imaging technique at the time could distinguish between 2 different kinds of water. And of special interest to me, and I think to those of us here at the Institute, is the object that Lauterbur worked with in 1973. We have the actual coconut that Lauterbur used as the subject to make the first 3-dimensional scan of an object. It's a little underwhelming in person, I hate to say it, but it's just a coconut. But you know, when you kind of tie it into this broader story, then it starts to take on a special meaning. Now, from a more practical standpoint, Lauterbur's method for producing an image from the raw data from the scan was not especially effective. And so it was a different scientist, Peter Mansfield at the University of Nottingham in the UK, who took Lauterbur's initial work a step further, using a mathematical technique called a Fourier transform to recover the desired image and greatly speeding up the imaging process. So by 2003, MRI had become ubiquitous in the United States, hailed as the most important medical imaging technology since X-rays. That year, Lauterbur and Mansfield shared the Nobel Prize in Physiology or Medicine for, as the prize committee put it, their discoveries concerning magnetic resonance imaging. But, of course, history is not that simple. Earlier in 1971, a medical doctor and a researcher working in Brooklyn named Raymond Damadian had published a paper in Science noting that when rat tissues were placed in a magnetic field and hit with a pulse of radio waves, the cancerous tissues emitted distinctly different radio signals than the healthy one, as a writer later put it. This raised the possibility that NMR could be used to study or to scan for cancer. Now, Damadian began to build an instrument that could make scans. His instrument made its first successful scan in July of 1977, a colorful image of the torso of his assistant, Lawrence Minkoff. And Minkoff is the slim one there with the wide tie right in the middle. Now, Damadian created a company named Phonar that introduced the first commercial MRI scanner in 1980. And as the medical utility of MRI became apparent, large firms like General Electric, Johnson & Johnson, Siemens, Hitachi, and Philips all introduced their own MRI machines. Damadian and Phonar promptly sued all of these firms for patent infringement, and eventually won significant judgments and settlements, though it took decades. It was into the 1990s. But Phonar did not end up thriving in this market, and today it has shifted to managing MRI centers and servicing existing scanners. Now, Damadian did receive a number of national level honors for his work with MRI. For instance, he and Lauterbur both received the National Medal of Technology from Ronald Reagan in 1988. But Damadian always felt wronged by the large corporations that dominated the medical device market and slighted by the scientific community. He felt Lauterbur had received too much of the credit for MRI, and Damadian donated his original MRI scanner, which he named Indomitable, and get a little sense of his personality from that, to the Smithsonian in 1989, where it was on display for a while. And he also lined up allies to write epic books like this one, 838 pages, 3.6 pounds, that really celebrate his role in creating MRI. And when Lauterbur won the Nobel Prize in 2003, Damadian was enraged. He took out a full-page ad in 6 different newspapers, including the New York Times, the LA Times, and a leading Swedish newspaper, proclaiming that the prize was a shameful wrong that must be righted. There were rumors floating around that perhaps Damadian's creationist beliefs had shaped the unwillingness of the committee, perhaps, to give him the Nobel Prize, or possibly that his long-standing feud with Lauterbur had contributed to the long delay in this. And it was only because Lauterbur was quite ill with liver disease that finally kind of forced the Nobel Prize Committee's hand to go ahead and award the prize in 2003. So I'm going to end by thinking a little bit about what we might learn from this history. Both Lauterbur's supporters and Damadian's fans have worked to try and shape the public memory of MRI. Lauterbur's wife, the scientist Joan Dawson, wrote a book of her own describing his role as the inventor of MRI. She donated his papers and that coconut to the Institute, perhaps a metaphorical counterweight to Damadian's donation of the Indomitable to the Smithsonian. I mean, we are a better museum, it's true, but you know, don't tell my friends who've moved up to the Smithsonian. But while the story of who gets appropriate credit was important to them, I'm actually more interested in what these complicated histories of instruments can tell us about the role of science in daily life. I'm fascinated by the movement of NMR from a molecular beam at Columbia to Varian in Silicon Valley and on to hospitals and even strip malls across the United States. Today, NMR is not only central to the sports pages, but it's also central to the stories that we're increasingly telling about our brains and what it is that makes us human. And I'm also been trying to sort of think about how to present NMR and MRI in our museum exhibits in the future. And that's something I would love to get your feedback on and your advice. What stories do you think we should tell about NMR as we try to reach out to the science-curious public? Thank you.
Roger, thanks very much. I know you have questions after that fascinating talk. So again, we want to take questions from our friends online. If you're online, you have a question, please type them into the chat. And Christine would be happy to share those with us. And we also have a microphone for those of our friends who are here in person. And so I invite you to step up to the mic and if you're here with us and share your question that way too. Does anyone here have a question, like to get the ball rolling? Bill.
Great talk, Roger. Nice to hear you again. Just reminded that it's not really MRI related, but a few years ago, Carsten Reinhardt, who is David's predecessor ×2, presented to the local ACS society about the development of NMR as an instrument. And key to that was Varian's support of John Roberts in doing research using NMR, and his volume of publications inspired or forced or coerced other scientists to enter that field.
Yeah, absolutely. Carsten's work is really fantastic and has really been central to the scholarship that's out there on the history of NMR. Yeah, I've really been enjoying learning from that, and I think that will really be central to the various ways you can talk and tell stories about the history of NMR.
Do we have any questions from our online friends? No, we're scrolling. Oh, we have another one here.
I just wanted to tell you about Lauterbur's story. I crossed paths with him a number of times. He's a great guy. But when I was pretty young, and he was older than me, I worked for Nicolay Instruments in Madison. And we made signal apertures and computers that acquired FIDs and did Fourier transforms. And they were some of the first computers that were used for analytical chemistry. He wanted us, the salesman took me down to meet him. And he said, "What do you know about two-dimensional transforms, Fourier transforms?" And I said, but I could look it up. And we didn't get that sale, but it was a couple of years or more after that we found out what he wasn't willing to tell us. I had even said, "Give me some data and we'll work on it." He wasn't gonna do that. So finally, he gave a talk at the Experimental NMR conference where he had put these two capillaries I think of water inside distilled water, but it doesn't matter. At any rate, so he had the image of these two little circles, and that was, to my mind, the first public, he later published it, explanation of what he'd been working on. And it took a while to realize he wasn't just trying to find where the capillary tubes were, that there was a lot more to what he had accomplished. And he got lots of prizes. He's a good guy.
Oh, yes. But yeah, it's great it's wonderful to hear that story, and fascinating to kind of get a sense of the personality, from people who met him and really interacted with him. I think one of the things that's marvelous about that, when he submitted that paper to Science, they complained that the pictures were really not clear enough. And he was like, it's the first time anybody's ever made a picture like this. So he was, later on, of course, he replied in a response that persuaded the editors, that this was persuaded the editors to do a further review, and the paper was eventually published. And later on, at the end of the 20th century, it was put together in a collection of Science's most influential papers of the century. And he liked to joke, that you could write a whole history of science from papers that had been rejected by journals.
Okay, what is the reason why the expression NMR changed to MRI?
Ah, yes, excellent, an excellent point. Nuclear fear, basically, right? So at least the story that's told is that recognizing that this was going to be a consumer-facing medical product, and the public's ideas about nuclear are nuclear bombs, dangerous, destructive, harmful radiation causing mutations, rather than magnetic stimulation of the nuclei of the atom. And so the thought was, well, we could just lose the nuclear part. We'll just call it magnetic resonance imaging. And magnets, they're friendly. We all have magnets around. So that would be a much more approachable label for it. Of course, one of the problems, right, is magnets are friendly, but in the scale and the intensity of the magnets that you need to produce an MRI image, they can be quite dangerous. And so, there's big warning signs, and it's something I would love to acquire for the museum, is one of these warning signs that says, don't come in here when you have, if you've got medical devices implanted in your body, and keep the metal out of the MRI room when the machine is operating. There's some amazing photographs online of somebody left a small a chair that had some metal in it that just wrecked the whole room when the MRI magnet was turned on, right? So yeah, there's kind of what's dangerous, what's not is an interesting discussion to have.
Marketing conundrum. Yeah.
From your research and discussions with different researchers, do you have a sense of what may be the next step in imaging?
I don't have a great sense of that. And I think that's, as a historian, I spend most of my time looking back, but I'd be interested to hear from the, people in the room what might be the next step from X-ray to MRI. What's the acronym to look out for?
Can you comment on the role of John Watt at?
We have a response to that.
Oh, I'm sorry.
Oh, no.
I'm an ophthalmologist, to be fair. So the next, I see the next area of imaging is OCT, ocular coherence tomography. That's totally non-invasive. And the resolution is incredible, as good as MRI, if not better. And you do this in the heart, you can do it in any tissue in the body. The one thing I caution everybody in this room to be careful of is you've got to remember that there's a difference between structure and function. MRI is a terrific tool, but it says nothing about function. And you're not looking at the active metabolism of the body with an MRI. You are with a PET scan, but not with an MRI. So you got to remember that's an important distinction to make when you're looking at these things. You can see people who have absolutely no symptoms and look terrible on MRIs and vice versa. So it's not 100%. You still have to use your brain. Unfortunately, nobody wants to do that. They want an image to take the place of your using your brain. And unfortunately, that's not the case. So I just caution everybody to, when you see one of these things, remember it's just an image. I have a question. How do they generate the image on the MRI? What is it? How do you get the electrons to produce an image on a photographic plate? Who discovered that? Was that those guys, the same guys?
It's my understanding is it's never been for an MRI. Yeah, my understanding is it's never been a photographic plate. It's always been a computer.
Yeah, I know, but somehow you have to make an image that's almost true. It's identical to the anatomy that you're studying. It's incredible. I mean, it really is that you're able to generate an image that's so good.
I actually can't. I'm afraid I can't answer that one, but it looks like we might have a person behind you who might. No.
No, I don't have an
Just a
answer.
question.
Oh, okay.
I have a question. Does anybody have an answer? Okay, I have a question. Why is the MRI so loud and what are all the different sounds that mean?
Gotcha. So, yeah, that's another one I don't have a totally great answer to. I mean, right, so we're talking about the scanner moving is part of it, but why it's so loud, I don't know.
So given the mass of the magnets that are necessary in order to do this, you can't create a perfect vacuum in order for them to functionally spin. And so as a result, you're hearing the very, very quiet clunking of a not quite perfect machine. I was actually curious to ask you about, as the rise of functional MRI becomes something moving from scientific research to actually being used, particularly in the brain, which I think was what you were alluding to, as well as our magnets become more and stronger. What do you think is going to be the next step in what we're looking at in the body? Like, for example, could it be metabolism? Could it be something having to do with the cells themselves?
Yeah, I mean, one of the things that I've been fascinated by, especially with the fMRI studies, is the fascination with localizing behaviors in the brain, and the repeated, at least in this, you know, and is this a distortion of how researchers are thinking of it, and how it gets translated into the public press, you know, the news outlets and things like that. But the incredible just sort of determination to say, okay, this is where this part of brain behavior goes on, this is where this happens, this is where this happens. That strikes me as not a particularly productive way to necessarily to sort of think about and understand brains, right? We know that people who have you know, various parts of their brain damaged can often you know, brains rewire themselves, they adjust, they find ways to compensate, right? And so as you're saying, you know, this questions of capability rather than structure are I think really interesting. And so what I would be really interested to know is how can we use that kind of insight to think about these kinds of non-invasive imaging technologies, right? So how do we need to use fMRI better to understand, you know, rather than just localizing these kinds of behaviors, to actually understand how they're going on kind of in distributed ways across the brain. That would be my answer, but I'm not a scientist in this.
We have another online question, I think.
What in your opinion, is the best book or books that discuss MRI?
Great.
Surely we have them.
Great question. Yes. I mean, Joan Dawson's biography of Lauterbur is really wonderful, which I think is Paul Lauterbur and the invention of MRI. That's really a good one. Carsten Reinhardt's kind of epic book, Shifting and Rearranging, is a fantastic from a scholarly point of view on the history of NMR.
She's got many more. So
Many more. Let's go with another online question so we're balanced accounts here.
When did the supercooled magnets from NMR and MRI2 become implemented?
Oh, that, I don't know that in terms of technical details of the history. I guess I'm assuming that is that like supercooling magnets, or just like way awesome? I don't know. Low temperature. Okay, makes sense.
yes, she has another one.
One more line, then I think we have a question over in this end of the room. Maybe we'll go with the online first and then we'll go ahead, Christine.
Did the various manufacturers take different approaches? What were they and which ones have prevailed and why?
That is another question I would love to be able to know the answer to. I will say this is relatively early in my kind of process of researching this topic. So I got really excited by the labels on the the instruments that we have here. We've been thinking a lot about what do we do with really large objects in our warehouse that we can't display or that we're not likely to display. And so it's kind of those historical questions that got me into this topic. In terms of thinking about the history of these instruments as they were commercialized in the 1980s and in the 1990s, that's not a place I've really looked too much. I will say that can be one of the more challenging places to get good perspective historically. And the 80s and 90s are also a bit of an interesting kind of a black hole where a lot of stuff is not publicly accessible. It was only came in print, so it's harder to access, right? Because a lot of that only appeared in print and then is not as so it's not necessarily digitally available in the same way. And so some of those probably would be really going to look at trade journals and medical instrument sales catalogs and things like that to answer that question. But I haven't done that research yet.
I think we had a question on this side of the room.
Thank you. Going back to the A-60, the machine that we have on display. Now, you may have gone over this, but I sort of have to ask this question. Did they use that on humans? And two, what did the graph actually signify? What did the instrument actually graph?
Okay. So they would not have. That would have been used. It would not have been used for humans. That would just be looking at had a pretty small opening for where you could put a sample. So it's measuring. So it's measuring the resonance of bonds or it's measuring the resonance of particular nuclei in there, right? So you're seeing spikes in the. Now I'm not sure if it's an absorbance or machine or not for the A-60, but yeah. So you're actually measuring the electromagnetic or the radio frequency waves coming back out from the sample.
An image from it, or is it just data?
No, it's a chart. You're looking at a chart. Here, I can. And so, yeah. So on the paper here, right? You have basically it's a specialized graph paper, and so it's manually writing out, or it's automatically writing out the spectrum. And so then you could go and you can see where your peaks in your spectrum are and compare that to a library of other, yeah. So in some ways this is an extension into the radio frequency realm of similar kinds of chemical fingerprinting techniques that were developed in ultraviolet spectrophotometry 20 years before. Yeah. Yeah, and that's, I mean, that's one of the really interesting things that I would love to be able to talk about in some interesting ways, like the production of these libraries, these spectrum libraries, so that, you know, and there are groups, some of which at the National Bureau of Standards, but at least for the case of ultraviolet spectrophotometry, the American Petroleum Institute in the 1930s was played a key role in sort of developing the libraries of spectrum of molecules so that they could be, that you could identify that. And that's a kind of easily forgotten, but really, you know, the instrument is here and kind of has a certain kind of charisma about it, but a big library of page after page after page of spectrum, while incredibly useful for scientists, incredibly dull for museum visitors. So how do you, how do you make that compelling and interesting? One of the kinds of challenges.
That's your next project.
that we have.
Christine, do you have another question for us from an online participant?
Yes. Can you comment on the role of John Watt, don't know if I'm saying that correctly, at MIT in the 1960s with respect to enhanced development of proton spectroscopy?
No,
Excellent answer.
but I know
We
somebody
might have
now I need
someone
to
up
look
front.
up.
We might have someone up front who can. Did you?
Ah,
Can we bring the microphone all the way back up? Because we've got a John Watt compatriot up front here who would like to speak to that question. We're making Risa walk everywhere. Here we go.
Oh, good.
Very good.
John Watt led a very significant research group at MIT and a lot of very significant research in various kinds of pulse sequences for doing sophisticated structure determination came from Waugh's lab. Of course, the one that everybody knows about was one that came from Alex Pines, who worked with John Waugh when they published a paper on magic angle spinning, which is if you spin that at a certain angle, then certain of the interactions get canceled out. But it was rejected because they didn't think that magic belonged in a scientific paper's name. So they rechristened it proton enhanced nuclear induction spectroscopy. And they got it through before anyone caught the joke.
what's that? What is the acronyms spell out there for?
It's a penis.
Oh, I see.
We've got more online.
More
Again, for
questions
asking for more
online. They
details.
keep coming. How do we top that?
You may want to get into it.
Can you say any more about our science history record of Mildred Cohn's MRI development and discoveries during their tenure at Britton Chance's Johnson Foundation from 1962 on?
Well, I can say that Mildred Cohn's oral history is really a delight to listen to. She's full of these stories about, she's a Jewish woman with a degree in science, a husband in science, and 3 kids, and about sort of how she navigated her life and building a career between these competing demands and the competing kinds of or the various kinds of exclusion and marginalization she experienced is it's dramatic, it's very powerful, and and she seems like her voice is really, really fascinating to listen to. So I would, this is another resource that our library team and our oral history team has done a great job in making that all. So there's a transcript. There's also, you can also listen to the oral history, the raw oral history, download pieces of the oral history if you're interested in incorporating it into a podcast or sharing just, it's a 5-hour long interview. So if you're interested in sharing pieces with your colleagues, with your students, that's all available in smaller chunks as well. So that's one of the things that we're really trying to do is make our oral history collection accessible to a wide range of people that might be interested to hear it and to learn from it, including some great technologies where you can sync up the for some of the newer oral histories where you can sync up the playback to the transcript. So you can go if if you read something interesting that you're like, oh, I want to hear what that person actually sounded like when they said that, you can go right from the transcript to the audio. I don't think that's true with Mildred Cohn's, but it's true for a lot of our oral histories.
Other questions online? Any other questions in the room? I think we have one over here, at least.
As Jim was alluding to, there's quite a galaxy of very talented people developing many things that in magnetic resonance. And there are two additional Nobel Prizes on the NMR side. One was Richard Ernst, who had actually worked at Varian, won it in '91 for multidimensional NMR. The second is Kurt Wittrick, who got it for protein structural determination, I think in 2002, something like that. And these people are all very interesting, but one time, just before Ernst won the Nobel Prize, he visited us at IBM. It was after he had won. And IBM had a huge problem producing disk drives. And it turned out this was stopping the shipment of all disk drives and tapes made by IBM in the plant. They couldn't, there was a head disk failure. And we used NMR to solve the problem. And what happened was they took, it was very slight debris was forming, like, what is it? It's very complicated. And they took 50 multi-million-dollar disk files, stressed them to failure, and then extracted these really tiny amounts of the debris. So you couldn't really see it. In my group, we ran the fluorine NMR, and we could tell what was causing the failure. This actually went to the chairman, so the product guys could say, we understand the problem. So now I'm meeting Ernst and I'm telling him, I've got something interesting to tell you about on what you helped develop, fluorine NMR, blah, blah, blah. And so he nodded when I told him the story, and he said, Bob, that's great. He said, Bob, that's great. You're being useful. And I just thought that was so droll and funny, He said, yeah, you're right. So a lot of interesting things in this space. And also John Waugh, I think, was a famously cranky person. So.
So did you find that NMR had a lot of kind of industrial applications or uses, other kinds of similar uses to that? That kind of story, I think, is really appealing for museum visitors.
Tremendously,
Yeah.
because as you were saying, the chemical environment of an atom and its nucleus depend on the structure, so you can tell what you have. And here, my example was in understanding failure in a very complicated, technology. Another example is when carbon-60 was discovered, the so-called Holy Grail was looking at the carbon spectrum of that. Since all the carbons are equivalent, you should see one resonance. And you do, and that confirms that it has this icosahedral symmetry. So it's hugely, important.
I think we have time for one more question, either online or in person. There's our candidate right in the middle of the room.
All right,
Risa.
sure thing.
Let me just say, by the way, that it's gratifying to have all the, not just excellent questions, but excellent contributions adding to the story. And let me invite those of you in the room and online post talk today. If you have anecdotes, stories, light that you can shed on this topic and you'd like to share that with us, please do email Roger. I'm sure he would welcome that, and be in touch with us at sciencehistory.org. And we'd love to collect information that way as well. So many thanks for adding to the story. Yes, sir.
So I don't have a question, but I do have an anecdote. I was a graduate student at the University of Wisconsin in Madison in the early 70s. And I heard this story that when the building first opened, just a few years before, an MRI machine was purchased for a lab on the 9th floor on a Friday afternoon. And when people returned to the building Monday morning, it was sitting in the lobby under a 9-story elevator shaft.
Oh, my goodness. Yes, indeed. Yeah, the stories of kind of, historians like to talk about big science as a kind of as a phenomenon of sort of the middle part of the 20th century, kind of, the growth of these huge research teams and very large kinds of equipment. And for museums and for other kinds of interpretive groups, that's a real challenge for how do we tell those stories of these big objects that are heavy and take up a lot of space, but are also, in some ways can be really transformative. And so that's, we've largely taken the strategy of let's take a piece of that instrument and show it. In our case, we just show the console. In the case of the Smithsonian, more and more they're interested in taking even smaller pieces. So we have a large chunk of very unusual steel that is in our warehouse that once shielded the Willard Libby's experiment that he used in sort of the development of carbon dating. And the Smithsonian got this nice, interesting, complicated set of radiation detectors that he could use to kind of filter out and exclude the coincidences of background radiation. But what we got instead was this huge metal shielding made largely of steel created before 1945, so that it wouldn't have absorbed any man-made radiation. And now it's too heavy to bring in the building, and so we're sort of, it costs us a few $100s every year to store it based on how heavy it is. And so we're sort of like, how do you interpret an object like that, right? Something that could fall through our own elevator shaft.
No competition for the coconut. So, well, thank you all for your questions, your anecdotes, your comments. Roger, thank you again for a superb talk. Please join me. Thanks, everyone. While we have you, and before those of us in person break for our reception, let me just alert you to a couple of happenings here at Science History Institute. On the screen, we're referencing our newest podcast. On Friday, February 3rd, we are launching Innate, How Science Invented the Myth of Race, which is a podcast and magazine project that examines the historical roots and persistent legacies of racism in American science and medicine. This event will be part of First Friday, our monthly First Friday program, the first Friday of every month. And that event will start at 5 p.m. In February. Please make sure to subscribe to our podcast series wherever you get your podcasts or through our website so you don't miss any of this series. Our next JPS, Joseph Priestley Society lecture, will be an online event, and that will be on February 23rd. So set your calendar to that. The topic will be, quote, alternative methods of drug delivery. So that's the next JPS lecture topic. And you can register online for that at sciencehistory.org. You can also support the Institute, more programming like this, by donating through our website, sciencehistory.org. And please also text us at text Science History to 44321, 44321, if you'd like to support tonight's program. Before we break for our reception, a reminder for those of you here that the museum will be open until 6:30 p.m. tonight. And thank you very much for attending. Hope to see you soon, either online or in person. Thanks so much all for being here. Thank you again.